Welcome to our presentation. Our topic of forecast will be the global plastic production per annum, sourced from our word in data.org. Upon plotting the data, we immediately notice the presence of an upwards trend, almost in the shape of an exponential. This is to be expected, given the common knowledge of how plastic pollution is devastating the planet on an unprecedented scale now more than ever. The highly variable nature of the trend indicates non-stationarity is present in the data. This visualization also confirms the lack of seasonality in changing variance. Additionally, there are no intervention points. Further tests confirm the stationary nature of the data, as Figure 1.1 shows the linear relationship between the latest recorded year and its predecessor. Additionally, the ACF 2.1 shows that there are significant correlations at every lag except for the last few. The significance of the lags gradually decays across the x-axis. This pattern is a strong indication of non-stationarity within the dataset. PACF Figure 2.2 has a significant correlation at lag 1, followed by correlations that are not significant. This pattern indicates an autoregressive term of order 1. Further numerical results from the hypothesis tests ADF, KPSS, and PP also indicate non-stationarity. Before addressing non-stationarity, we ran multiple checks and confirmed that our dataset did not pass normality assumptions. Attempts were made to transform the dataset and rectify this, but no method prevailed. Methods tried include the Box-Cox transformation, reciprocal transformation, and squared/square root transformation. So we moved on to difference in the data, which enabled us to achieve stationarity on the second difference. Figure 3.2 and 3.3 possess a couple of significant lags, but ultimately they do not have the same pattern as before, indicating stationarity has been achieved. 3.1 shows the trend wave is roughly around the mean line, and the numeric hypothesis test from before now all indicate stationarity.
Once we have achieved referencing of our data and identified that the data is in fact stationary, we move on to model specification. By using the EACF and ARIMA subsets functions provided by R, we can narrow down our set of possible models to a manageable size. In the EACF graph, we observe a cluster of O's that make for valid ARIMA models, being ARIMA 122, 123, 222, and 223. We additionally select ARIMA 023 and 322 for extra security that the awkward bounding of the x's could be accounting for other models. Next, we use the ARMA subsets to identify other possible models that the EACF may have missed out. Here we take the first three rows, which constitute an ARIMA 224, 523, and 222 model. In total, we have identified an ARIMA 122, 123, 222, 223, 023, 322, 224, and 523 model may be used. After identifying a set of possible models, we store them as ARIMA models with their respective terms. Each ARIMA model is composed of two different method types, CSS and ML. Using the CoF test function, both methods for each model are executed to determine which methods work and if a model is redundant. Through this process, we further narrow a model selection to ARIMA 122, 123, 222, 223, 023, and 322. Because different models respond differently to either ML or CSS, the final models used a combination of ML and CSS instead of choosing only one ML or two CSS. We then run the sort.score function on these models for both the AIC and BIC scoring criteria and pick the model with the lowest values. In this case, the AIC and BIC recommend two different models being ARIMA 023 and 223. Because BIC is considered to be more rigorous scoring criteria for model selection, we select ARIMA 023 as our forecast model over the ARIMA 223 model. Residual analysis is then conducted over our ARIMA 023 model. 5.1 indicates a degree of randomness to the standardized residuals if we ignore the single outlier over here. The distribution, 5.2, seems to be normal as well, with only one major outlier being present. The QQ plot, 5.3, indicates normality as we would expect by following the line and tapering off at the ends. The ACF and PACF only have one significant lag, and further tests conducted with the Jung box test indicate that these are insignificant, along with our potential residual correlations. Additionally, this same test was run on the former AIC top pick, ARIMA 223, and differences were found to be minimal. This further strengthens our resolve to adopt the ARIMA 023 as our main method of forecasting.
After we fit the model in the original dataset, it appears to soundly predict the next 10 years of plastic pollution. However, it appears to be linear and lacking an autoregressive nature, which is to be expected as the AI order is set to 0. Ideally, the prediction should exponentiate as the rest of the trend does, but perhaps our inability to address normality issues has caused this fallacy. Thanks for watching.